Now let us apply the Schrodinger wave equation to a rigid rotator model. I have already defined rigid rotator model in the previous video, so I will not explain it in greater detail again, okay, but I will explain it in very simple way. So why this rigid rotator model is important? It is important because it is quite useful in describing the rotational energies and thereby the rotational spectroscopy of diatomic molecules. So in a rigid rotator model, you have two atoms or two particles of masses m1 and m2 rotating about the center of mass. Okay, so this point represents the center of mass. Okay, the distance between the two atoms is r1, which is nothing but the equilibrium distance called as bond length, and here we are assuming that the distance between the two atoms remains the same, that is the bond length is fixed as the molecule rotates. So value of r is fixed, and therefore this model is called rigid rotator model. R1 and R2 represents the distance of the two atoms from the center of mass, and the reduced mass of such system is given by mu is equal to m1 into m2 divided by m1 plus m2, and the distance relationship is r is equal to r1 plus r2, and we are assuming that this molecule can rotate freely in along any axis in 3 dimension. Okay, so this rotation can happen in any axis, not just this vertical axis, it may even happen in horizontal axis. Okay, so this is one type of rotational motion. Even the molecule may be rotating like this, or the molecule may be rotating like this. So the direction of this axis can be fixed in any orientation. So all possible rotations in 3 dimensions are allowed. So what we will do is we will use a 3-dimensional Schrodinger wave equation. So let us first write the general 3-dimensional Schrodinger wave equation. The 3-dimensional Schrodinger wave equation, the general equation is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square m by h square into E minus V into psi is equal to 0. This is the general Schrodinger wave equation, and we are using the 3-dimensional one because we are considering the all possible rotation of the molecule along any axis in 3 dimension. So for a rigid rotator model, the mass is replaced, m here, mass of the particle is replaced by the mass of a hypothetical particle, okay, that is reduced mass mu. I already told you in the previous video, we are replacing a two particle problem by a single particle problem where we have a hypothetical particle of mass mu. So for a rigid rotator model, the mass is replaced by reduced mass, and since the rotation is free rotation, it means there is no hindrance for the rotation of the molecule, so the potential energy remains constant, and we take that constant equal to 0. Okay, so for free rotation, there is no hindrance for the rotation. Okay, there is no opposition for the rotation of the molecule, so it is a free rotation. It means the potential energy for rotation is 0, and we take constant, and we take that constant equal to 0. So these are the conditions for rigid rotator model. If I supply this substitute this condition in the Schrodinger wave equation, we can write the Schrodinger wave equation for rigid rotator. Therefore the Schrodinger wave equation for rigid rotator is dou square psi by dou x square plus dou square psi by dou y square plus dou square psi by dou z square plus 8 pi square mu divided by h square into E minus 0. So into E into psi is equal to 0. Okay. Okay, I will follow the same equation numbers that I have used in the notes. So this is equation 1, this is equation 2. Okay, so this is a 3-dimensional Schrodinger wave equation where psi is psi of x comma y comma z. Okay, the wave function is represented in terms of the position, the Cartesian coordinates of the particle's position x, y, z. Now, since this motion is not a linear motion, it is a rotational motion, it is always convenient and helpful or useful to express the position of the particles in polar coordinates rather than Cartesian coordinates. Okay, I will repeat. Since the motion is a rotational motion, it is always better to express the position of the particles, rotating particles, in polar coordinates rather than in Cartesian coordinates. Cartesian coordinates are better suitable for linear motion, whereas polar coordinates are suitable for rotational motion. So what are the important aspects of these polar coordinates? Let us see. Okay, so equation 2 is the Schrodinger wave equation. It is expressed in Cartesian coordinates. Okay, so what do you mean by Cartesian coordinates? You have three mutually perpendicular axes, x-axis, y-axis and z-axis. So this is the origin. Okay, this is y, this is x and this is z-axis. So if I have some particle here in out of the plane of this board, okay, so it is a three-dimensional picture mapped in a two-dimensional board. So this particle is actually above or in front of the board. Okay, so what I do is I have two particles. One particle of mass m1, it is kept at origin, and the other particle is in space somewhere here, m2. Okay, it is expressed, its position is x, y, z. Its position is 0 0 0 because it is at the origin. So one of the particle is placed at the origin, the other particle is in the space somewhere here, and this particle is rotating, okay, about this point. Now we know the distance between these two is fixed, it is equal to r. So here I have expressed the position of the second particle in terms of three distances: distance of the particle along x-axis, y-axis and z-axis. Okay, so this distance, okay, so this distance is the z distance of the particle m2 from origin. Okay, if I drop a perpendicular into the xy plane, okay, this is perpendicular, this is perpendicular, so this distance is x and this distance is y, so this is also x, this distance is y. Okay, so what we have done here is we have expressed the position of the particle in three distances, in terms of three distances: distance along the x-axis, y-axis and z-axis. So that is why we have written as x comma y comma z. But what we do in spherical coordinate or polar coordinate is we are expressing the position of the particle in terms of one distance r, that is the distance of the particle from the origin, and in terms of two angles theta and phi. So Cartesian coordinates contain three distances x, y, z along x-axis, y-axis and z-axis. In polar coordinates we express in terms of one distance r, that is the direct distance of the particle from the origin, and two angles theta and phi. Since we have angles theta and phi, this polar coordinate is a better way of expressing the rotational motion, because rotational motions are more expressive in terms of angles rather than distances. So let us try to define what are these three variables r, theta and phi, and what is the relation between the Cartesian coordinate x, y, z and the polar coordinates r, theta and phi. Okay, so I will erase this to make things clear. Okay, so I already told you r is the direct distance of the particle from the origin. Let us define what is angle theta and phi. The angle theta is this angle. It is the angle between this vector joining the two particles and the z-axis. So that angle is theta. The angle phi, this is the original vector representing the distance of the particle from the origin. What I have done is I have dropped a projection along the xy plane. So this line, if I take this as point P and this is point P dash, so OP dash is the projection of OP in the xy plane, and this projection line OP dash makes an angle with x-axis, okay, and that angle is called as phi. Okay, so this angle, when this particle moves in 3 dimension along xy plane, this projection also moves in the xy plane, and therefore this angle phi varies. If this particle is moving like this, okay, it means its angle with the z-axis changes, it means theta changes. If the particle is moving away from the origin, it varies r. So if the particle is moving away from the origin, r varies. If the particle is rotating like this, theta varies. If the particle is rotating like this, okay, then the value of phi varies. Okay, so this is how we define r, theta and phi in polar coordinates. And by using trigonometric relation, you can find out what is the relation between x, y, z and r, theta, phi, which we will not prove here. We will directly take the result, which you have to memorize. X is given by r sin theta into cos phi. Okay, this is the relation between x of the Cartesian coordinate with r, theta and phi of the polar coordinate or the spherical coordinate. Y is r sin theta into sin phi. Okay, almost the expressions are one and the same. The only difference is here you have cos phi, here you have sin phi. Z is somewhat different. It is r into cos theta. So these are the three relations, okay, between the Cartesian coordinate and the polar coordinate. And the range in which we can vary the values of r, theta and phi should be known. In Cartesian coordinate, x, y, z can be varied from minus infinity to plus infinity. In the polar coordinate, r varies between 0 and infinity. Suppose if this particle is at origin, it means r is equal to 0. As this particle moves away from the origin, the value of r increases and theoretically it can reach maximum value of infinity. Phi, okay, which represents rotation, the lowest value is 0 and the maximum value is 2 phi. If the particle completes one rotation, the angle covered would be 360 degree. So the maximum value of phi is 360 degree, that is 2 pi. The value of theta is between 0 and 180 degree. Okay, so why it is not 360 degree? There is a reason behind it which I will not explain here. All those are mathematical explanations which I will skip here. So the value of theta varies between 0 and pi, or you can do the other way also. You can fix the value of phi between 0 and pi and fix the value of theta between 0 and 2 pi, but these are the conventional ways of fixing the limits. So these three terms represent the relation between Cartesian coordinate and polar coordinates, and these are the limits within which the values of r, theta and phi varies. So what we do is we use these relations and try to convert this Schrodinger wave equation from Cartesian coordinate into polar coordinate. What is the purpose of converting the Schrodinger wave equation from Cartesian coordinate to polar coordinate? Because as I already told you, the rotating systems are better expressed in terms of the polar coordinates. So let us now rewrite equation number 2 into another equation, equation number 3, where the Schrodinger wave equation is expressed in polar coordinate. Okay, equation 2 in polar coordinate system is, okay, how to convert this equation from Cartesian coordinate to polar coordinate. We will avoid all those mathematical steps. We will directly write the final results, which unfortunately you have to memorize. The expression is 1 by r square into dou by dou r into r square dou psi by dou r plus 1 by r square sin theta into dou by dou theta of sin theta into dou psi by dou theta plus 1 by r square sin square theta into dou square psi by dou phi square. Okay, so the first three terms in Cartesian coordinates are written now in terms of polar coordinates, plus 8 pi square mu into e by h square into psi is equal to 0. So equation 3 is the Schrodinger wave equation in polar coordinates for the rigid rotator model. And here the wave function psi is actually psi of r comma theta comma phi. Here psi was expressed in terms of Cartesian coordinate, now psi is expressed in terms of polar coordinate. So equation number 2 or equation number 3 is a three-dimensional Schrodinger wave equation. But if you carefully look at this equation, okay, since the model is a rigid rotator model, what do you mean by rigid rotator model? The value of r is fixed. So since the value of r is fixed, this term becomes equal to 0. So the first term of this differential equation becomes 0 since r is fixed and r is not a variable. Since r is fixed for a rigid rotator, that is, it is a constant, not a variable, the first term in equation 3 becomes 0. The first term in equation 3 becomes 0. So we can simplify the differential equation 3 and write, okay, so equation number 3 can be written as 1 by r square sin theta into dou by dou theta of sin theta into dou psi by dou theta plus 1 by r square sin square theta into dou square psi by dou phi square plus 8 pi square mu into e by h square into psi is equal to 0, where now psi depends only on theta and phi. So equation number 4 is a partial differential equation consisting of two variables, and this equation is solved by the method of separation of variables. So what is the assumption we make in the method of separation of variable? Equation 4 is solved by the method of separation of variable. That is, we are assuming that the overall function psi of theta comma phi can be expressed as product of two functions. First function capital T depends only on variable theta. The second function capital F only depends on variable phi. Okay, so this is the assumption that we make in the method of separation of variables. So if we substitute this equation 5 in equation 4, okay, we already know what would be the result. Okay, we applied this method in particle in a three-dimensional box. So when I apply this method of separation of variable to a three-dimensional problem, this three-dimensional problem gets simplified and converted into three one-dimensional problem. So here you have a two-dimensional Schrodinger wave equation. If I apply this method of separation of variable, the two-dimensional Schrodinger wave equation will be converted into two one-dimensional Schrodinger wave equations, each equation dealing with one variable here. So you get two equations, one equation dealing with variable theta, the other equation depending or dealing with variable phi. Okay, so substituting equation 5 in equation 4 and simplifying. How to simplify? We will avoid all those mathematics that are not required, and simplifying, 1 obtains two separate equations, each equation dealing with only one variable. What are those two equations? We will directly write the result. You have to memorize these equations, unfortunately. First equation is minus 1 by f into b square f divided by d phi square is equal to m square. Okay, this equation deals with only one variable phi, where this f denotes function f of phi. And the other equation is sin theta divided by t into d by d theta of sin theta into d theta dt divided by d theta plus 8 pi square I into e divided by h square into sin square theta is equal to m square. 8 pi square e pi h square into sin square theta is equal to m square. Equation number 7, where t denotes the function t of theta. So here we are introduced to this quantity I, which is nothing but the moment of inertia of the rigid rotator, which is given by I is equal to mu into r square, where mu represents the reduced mass. So we here come across a new term called m square. This m square is nothing but a separation constant. This is a routine constant that we generally obtain when we apply the method of separation of variable. Okay, so this is a mathematical result that whenever we apply the method of separation of variable and try to separate the variables, we end up with getting a constant, and that constant is called a separation constant. So m square is a separation constant. What is its value? We do not know yet what is the value of m square, but we know that it is a constant called separation constant. Okay, so m square is called as separation constant. M square is called as separation constant. Now let us try to solve these differential equations. Again, we will skip the mathematical details of how to solve these differential equations. They can be solved by simple mathematical steps or methods, which we will skip. The solving equation, differential equation 6, we get the normalized solution, okay, by applying boundary condition and by applying normalization condition, as we did for Schrodinger wave equation for particle in a one-dimensional box. Here also, while solving this differential equation, we apply the boundary conditions and the normalization condition and try to solve this equation, and the solution is f, which is nothing but f of y is equal to 1 by square root of 2 into pi into e to the power I m phi. Okay, so this is the solution one obtains when this differential equation 6 is solved. Okay, and this is a normalized solution, and the value of m, okay, is restricted to take only plus or minus integral values up to infinity, and there is a restriction on the value of m that it can only take integral values, but there is no limit on the maximum value. It can take any value up to infinity. Why this restriction we have? This restriction is because of the boundary condition or the normalization condition. Okay, this is so one type of quantum number. Now let us try to solve equation 7. So before solving equation 7, what we will write is rewrite that equation. Rewrite equation 7, sin theta divided by t into d by d theta of sin theta into dt by d theta plus this term which is a constant for a given molecule, I will take it as beta into sine square theta is equal to m square. Equation number, okay, I have made a mistake in the notes. Okay, I'll take it as equation number 8 dash. Okay, a mistake in the equation number in notes. Okay, I'll take it as 8 dash, where beta is 8 pi square I into E divided by h square. For a given molecule, this is a characteristic value. Okay, beta is equal to 8 pi square I into E by h square. Now let us solve this differential equation 8 dash. Again, we will not go into all the mathematics. We will directly write what is the normalized solution. So by applying the normalization condition and by applying the boundary condition that is applicable for this equation, we can obtain the normalized solution. And the normalized solution for equation 8 dash, normalized solution for 8 dash is t is equal to t of theta is equal to square root of 2 into j plus 1 into j minus mod m whole factorial divided by 2 into j plus mod m whole factorial. Mod m means absolute value of m into a polynomial, mathematical polynomial represented by the symbol p, which depends on this number j, called as a rotational quantum number, and it also depends on the absolute value of the another quantum number m into cos theta. Okay, so these equations are rather lengthy and complicated, but we have no option rather than memorizing this equation. Okay, so here j is a constant and it is called as rotational quantum number. For a given state it is a constant, but as the state of the system changes, it also changes. So j is called as rotational quantum number, and its value is restricted to take positive integral values, and the value of m, okay, which was restricted to take integral values, is now further restricted here because of the additional boundary conditions. Its value is 0, plus or minus 1, plus or minus 2. Maximum value it can take is plus or minus j. So here it was assumed that it can take values up to infinity, but here there is a restriction that it can take only values up to plus or minus j. So this quantum number m has not much significance here, but it has a very important significance when we discuss the rotational motion of the electron around the nucleus. So when we discuss hydrogen atom, we will concentrate on this quantum number m. So here we are interested in only this quantum number called as rotational quantum number represented by j, and this polynomial p j m is called Legendre polynomial. Okay, it is called as Legendre polynomial. It is a polynomial of degree j and order mod m. Okay, we will not go into the mathematics of this. Okay, so it is some sort of polynomial. What we are interested in, just the final expression for the wave function and the final expression for energy. So therefore the total wave function, if you go back to the method of separation of variable equation, the total wave function psi of theta comma phi is t of theta into f of phi. Therefore the total wave function psi of theta comma phi is equal to, if I multiply equation number 8 and equation number 10, we get the total wave function. It is 1 by square root of 2 pi into e to the power I m phi into square root of 2j plus 1 into j minus mod m factorial divided by 2 into j plus mod m factorial into polynomial pj into cos theta. If I combine these two square root terms, we get the final expression for the wave function of rigid rotator model. Okay, therefore psi of theta comma phi is equal to, if I combine these two square roots, it becomes square root of 2j plus 1 into j minus mod m factorial divided by, here you have 2 pi into 2, so 4 pi into j plus mod m factorial into polynomial pj into cos theta. Okay, so this equation I have missed in the material that I have given. You have to write it. This is the expression for the total wave function of a rigid rotator, which I'll take it as equation number 10 prime or 10 dash. Okay, so this is the overall wave function, which is called as spherical harmonics. Okay, so this type of wave functions are called as spherical harmonics because they depend only on sorry, I missed one important term, into e to the power I into m phi, this term. Okay, e to the power I into m phi. So this is called as spherical harmonics because this wave function depends only on the angular variables theta and phi. It does not depend on the distance. Such type of functions are called as spherical harmonics. We will discuss about spherical harmonics when we discuss the Schrodinger wave equation for hydrogen atom. Now let us find out what is the rotational energy of a rigid rotator. We will not go into the detailed derivation of the expression. Okay, I already showed that the beta value is 8 pi square I into E divided by h square. Okay, equation number 9, which is a characteristic value for a given molecule. So it can be shown that the value of beta is also restricted from the boundary condition and the normalization conditions. When we apply those conditions, it can be shown that the boundary conditions and normalization condition even restricts the value of beta. Beta can take only values equal to j into j plus 1, where j is the rotational quantum number. So this is the condition that restricts the value of beta to only have values j into j plus 1, and even we know that the j values are restricted to integral values. So if we compare equation 9 and 10, comparing equation 9 and 10, we get 8 pi square I into E divided by h square is equal to j into j plus 1. So if I rearrange this equation, one can write an expression for the energy of the diatomic molecule which is behaving as a rigid rotator. So the rotational energy, therefore the rotational energy of the rigid diatomic molecule is E is equal to, if I rearrange it, it becomes h square divided by 8 pi square into I into j plus 1. I use the subscript j because the value of energy depends on the rotational quantum number. So this is the expression for energy which you have already encountered in the spectroscopy, where you discussed the rotational spectroscopy of a diatomic molecule by treating it as a rigid rotator. So now we know how we obtain this expression for energy. It is obtained by applying the Schrodinger wave equation. This is a constant for a given molecule because h square, 8 pi square are universal constants. I, the moment of inertia, is a constant for a given molecule. So this can also be written as Ej is equal to some constant B into j plus 1. Okay, this constant B is h square divided by 8 pi square I, expressed in the units of joules. Okay, probably you have used a quite different expression for this B in spectroscopy, because there we have expressed B in centimeter inverse unit. Here we have expressed B in the unit of joules. So this B is nothing but called as rotational constant of the molecule. It is a very important constant related to the rotation of the molecule. Okay. So this is the expression for energy, and this is the expression for the wave function for a rotating diatomic molecule treated as a rigid rotator. To sum up this uh, topic, let us try to understand some important features of rotational energy of a diatomic molecule. Okay. The first observation that we can make is the value of J, that is the rotational quantum number, is restricted. J can take only integral values. So since the values of J are restricted, the values of Ej are also restricted. It means a molecule rotating can rotate with only certain amount of energy. It cannot have all the types of energy. It can have only certain values of rotational energy depending on the value of rotational quantum number J. It means the rotational energy of the molecule is discrete, or it is quantized. So the first observation is rotational energies are discrete, or they are quantized. So just like the energy of the particle trapped in a one-dimensional box, the energy of a rotating diatomic molecule is discrete or quantized. That is why they are useful in rotational spectroscopy, because the rotational energies are quantized. The second observation or feature is about the lowest energy the molecule can take upon rotation. The lowest rotational energy is obtained by substituting lowest value of J. What is the lowest value of J? J is equal to 0. So if I substitute J is equal to 0, Ej will be equal to 0. So the lowest rotational energy a particular molecule has is Ej is equal to 0 when J is equal to 0. So since the lowest energy is 0, it means therefore there does not exist a 0 point rotational energy. For a particle trapped in a one-dimensional box, the lowest possible energy is non-zero. So we said that there exists a 0 point energy, but here the lowest energy is 0. Therefore, there does not exist a 0 point energy, or rather 0 point rotational energy. The third observation is about the gap between the energy levels. So let me draw the energy level diagram for the rotational energy. The lowest energy the particle has is when J is equal to 0, and that energy Ej or E0 is 0. The next possible energy that rotating molecule can have is when J is equal to 1. Okay, so J is equal to 1. The energy is E1 is, so if I substitute J is equal to 1, so 1 into 1 plus 1, that is 2 into B. So the energy is 2 times the rotational constant. The next possible energy is when J is equal to 2, and it is 2 into 2 plus 1. 2 plus 1 is 3, so 2 into 3 is 6 times B. So the next energy is when J is equal to 2, and the energy E2 is 6 times B. The next possible value of J is 3. So in that case, 3 into 3 plus 1, 3 into 4, 12B. So the next possible energy is somewhere here. Okay, I will draw somewhere here. So E3 is equal to 12b when j is equal to 3. So what do we observe? That as the value of j increases, as the value of j increases, the energy gap delta E also increases. Delta E also increases. So here the delta E was equal to 2b. Here delta E, the separation is 6b minus 2b, that is 4b. Here the spacing or the energy gap delta E is 12b minus 6b is equal to 6d. So as the j value increases, the energy gap also increases. So what does it mean? It means that rotational energies are not equally spaced. So these are some of the important characteristic features of the rotational energy of a rigid rotator. Of course, I hope that you have studied these expressions and the meaning of this expression in greater details in the rotational spectroscopy. So I will not again go into all those aspects again. It will be redundant if I talk all those things again here also. So these are some of the important characteristic features of rotational energy. One, it is quantized. Second, there does not exist 0 point rotational energy, and the rotational energy levels for a diatomic molecule treated as a rigid rotator are not equally spaced, they are unequally spaced. So this is about the application of Schrodinger wave equation to rigid rotator model, which is useful for describing the rotational spectroscopy of a diatomic molecule. In the coming class, we will apply the Schrodinger wave equation to another model called the simple harmonic oscillator model, which is useful to describe the vibrational spectroscopy of a diatomic molecule. Okay, so please go through both the videos. One is the video related to application of Schrodinger wave equation to rigid rotator model, and the previous video where I discussed some basic concepts of one particle and two particle rotating system. We will discuss about this in the coming class, in the live class. Okay, until that, please go through both the videos. Thank you.